Discover how powerful heavy machines shape the world's biggest construction projects with precision, strength, and innovation. The Honam High-Speed Railway, one of South Korea's major infrastructure projects, demonstrates the nation's advanced bridge construction technology through the use of the precast segmental method. This technique, applied in the construction of the Mangyang River Bridge within Section 3-3 of the project, represents a highly efficient and precise approach to building railway viaducts for high-speed trains. The system is characterized by the factory production of pre-stressed concrete box girders, each 25 meters long, which are then transported and installed at the site using specialized lifting and launching equipment. The PSM technique ensures the highest possible construction quality through complete industrialization and mechanization of the process. In traditional bridge construction, concrete casting and curing are performed on-site, which exposes the structure to environmental variables such as humidity, temperature, and uneven curing conditions. In contrast, the PSM approach allows each box girder to be fabricated in a controlled factory environment where temperature, vibration, and concrete mix proportions are strictly monitored. This not only enhances structural strength and dimensional accuracy, but also reduces potential human error and material waste. Each 25-meter box girder is a hollow rectangular beam designed to support both the track structure and the dynamic loads of high-speed trains. After production, the girders are carefully inspected and stored until the site is ready for installation. Transportation to the construction site is carried out using special multi-axle trailers capable of carrying heavy loads over long distances without deformation. Once at the site, large-scale cranes or launching gantries are used to lift the girders and position them precisely on the piers. The installation sequence is carefully planned to ensure both safety and efficiency. Before the girders are placed, the bridge piers are constructed and aligned with millimeter-level accuracy. Temporary supports or bearings are installed on top of the piers to receive the box girders. Once the girders are set, they are adjusted to achieve the designed alignment and level. Afterward, adjacent girders are connected using post-tensioning cables, which compress the segments together, allowing them to behave as a single continuous structure. This technique minimizes the formation of cracks and increases the bridge's ability to withstand dynamic forces during train operation. One of the main advantages of the PSM method is the significant reduction in construction time. Since the production of girders in the factory can proceed simultaneously with foundation and pier work at the site, the overall schedule is greatly shortened. In addition, the on-site assembly process is faster and less dependent on weather conditions. The high degree of prefabrication also improves work safety, as less manual labor and formwork installation are required on elevated structures. From an engineering perspective, the PSM system provides outstanding precision and quality assurance. The use of advanced equipment such as automatic concrete mixers, curing chambers, and precision molds guarantees consistent dimensions and surface finish for each segment. Furthermore, the controlled pre-tensioning process enhances the durability of the structure, reducing long-term maintenance needs. The mechanized erection process using gantry cranes and synchronized lifting systems ensures accurate placement without the need for extensive scaffolding or falsework, making it ideal for long-span viaducts crossing rivers and urban areas. Environmental benefits are also achieved through this method. Since most operations are concentrated in the factory, noise, dust, and waste generation at the construction site are minimized. The reduced on-site concrete pouring helps protect nearby waterways and ecosystems. Moreover, optimized material usage and transport logistics contribute to the sustainability goals of modern infrastructure projects. The success of the Mangyong River Bridge construction under the Honam high-speed railway project highlights the advantages of adopting industrialized bridge construction technologies. By combining precision engineering, advanced materials, and automated processes, the PSM method delivers structures that are not only strong and durable, but also aesthetically refined and environmentally friendly. Ultimately, this approach exemplifies South Korea's commitment to innovation in transportation infrastructure. The Honam high-speed railway, built using the precast segmental method, achieves both superior structural performance and efficient project execution. It stands as a model of how advanced prefabrication techniques can transform large-scale bridge construction, ensuring safety, quality, and speed while contributing to the nation's sustainable development. The process begins with preparing the trench where the concrete drainage pipes will be installed. Using a Caterpillar 320C excavator, the operator carefully digs the trench according to the required depth, slope, and alignment specified in the drainage plan. The excavated soil is moved aside to keep the work area clear. The base of the trench is then leveled and compacted to ensure stability and proper water flow. Any loose materials are removed before placing a bedding layer of sand or gravel for uniform pipe support. After the trench is properly prepared, the installation of the concrete drainage pipes starts. The Caterpillar 320C excavator uses strong lifting chains attached to its bucket to carefully raise each heavy pipe section from the ground. With precise movements, the operator lowers the pipe into the trench, while workers on the ground guide it to the exact position. Each pipe is connected end to end, ensuring the joints are properly sealed with rubber gaskets or mortar to prevent leakage. The alignment and gradient of the pipes are checked continuously to maintain smooth water flow. After all pipes are laid, the joints and bedding are inspected for accuracy and stability. The trench is then partially backfilled with selected material around the sides of the pipe to secure its position. Finally, the remaining soil is filled and compacted in layers to restore the surface. The completed drainage line ensures efficient water discharge and long-term durability of the underground system. In Edmonton, Alberta, a team of the toughest and most skilled ironworkers took on one of Canada's most ambitious engineering challenges, the construction of the new Walterdale Bridge. These ironworkers, members of Local 720, worked under extreme conditions to replace a century-old bridge with a modern, state-of-the-art structure worth over $150 million. Their task demanded not only physical strength, but also precision, courage, and teamwork in one of the world's most dangerous trades. The Walterdale Bridge project was unique in both scale and complexity. The centerpiece of the bridge, a massive 1,000-ton steel arch, was built on land and had to be floated up the North Saskatchewan River on barges before being lifted into place. Every step of the process required meticulous planning. The ironworkers faced immense time pressure as the freezing Canadian winter threatened to shut down the river and delay the project by months. With ice forming rapidly, they had only a short window to move and position the bridge before nature closed in. Before the massive arch could be transported, the crew had to assemble a temporary steel framework called the red iron, red-painted falsework, designed to support the bridge until it could be fully secured. This task involved connecting heavy steel beams high above the river. For men like Bo, a veteran ironworker, climbing 56 meters into the cold air to bolt slippery steel braces together was both nerve-wracking and exhilarating. Despite injuries, close calls, and the constant risk of falling, these men continued to work, driven by pride in their craft and the knowledge that future generations would cross a bridge they built with their own hands. Each day on the site demanded absolute concentration and coordination. Even the smallest mistake, an eighth of an inch misalignment at the base, could mean several inches of error at the top, threatening the structure's stability. That's why teamwork was vital. Welders, fitters, crane operators, and riggers had to synchronize every move. Despite the intensity, humor and camaraderie kept spirits high. Iron workers are known for their rough jokes and sharp banter, an essential survival mechanism in such a high-pressure environment. Before the arch could be lifted, engineers and ironworkers had to test the barges that would carry it. Andreas, one of the supervisors, was in charge of positioning the barges in shallow, unpredictable waters. During testing, they discovered rocks and debris under the riverbed that could cause the barges to get stuck. Dredgers were called in to deepen the channel, and the crew waited anxiously as machines worked through the night. The next morning, after hours of freezing labor, the barges were ready to move. Floating a 1,000-ton bridge section up a river surrounded by ice was a monumental task. The structure was placed on greased skid shoes and carefully slid from land onto the barges. Every movement had to be controlled with winches and cables to prevent instability. The crew watched nervously as the massive steel arch began to inch forward. But then, the barges got stuck again and there wasn't enough water under them. With no other choice, dredging continued while the temperature dropped further. Time was running out, and the growing ice threatened to trap the bridge until spring. After several tense days, the crew finally received clearance to move the structure. At 5 a.m., in sub-zero temperatures, the ironworkers gathered in full survival suits. "If this thing goes down, it's like the Titanic," one of them joked grimly. The barges began to move, winched slowly upstream through chunks of ice. The atmosphere was electric. Everyone knew that one wrong move could mean disaster. The ice pressed against the barges, the cables groaned, and the cold bit deep, but the men held their course. Meanwhile, other crew members were still hard at work preparing the landing supports for the skid shoes on the south shore, where the arch would finally rest. Timing was critical. As the barges approached, the workers on land synchronized their efforts to guide the structure into its exact position between the two towers. The entire operation depended on millimeter precision. Slowly, the arch was maneuvered into place. Engineers checked alignment, and when the structure finally touched down on the skid shoes, a wave of relief spread through the crew. The welders quickly got to work securing the bridge, and bolts were tightened one by one. The most dangerous phase was over. Cheers broke out across the site as months of pressure and exhaustion gave way to triumph. The pride was visible on every face, a mix of fatigue, satisfaction, and awe at what they had achieved. The Walterdale Bridge project was not just about steel and rivets, it was a testament to human endurance and teamwork. Every ironworker on that site faced fear, cold, and exhaustion, yet none backed down. They worked through pain and danger, balancing skill and bravery every step of the way. To them, it wasn't just another job, it was a legacy. In the end, despite delays, ice, and countless obstacles, the Walterdale Bridge stood tall over the North Saskatchewan River, a graceful arch of steel symbolizing the strength and determination of those who built it. For the ironworkers who risked their lives on that frozen river, it was more than just a structure. It was proof of their craftsmanship, courage, and unity. The bridge became a landmark not only for Edmonton, but also for every ironworker who dreams big, builds strong, and never quits. The 183-foot-long, 226,000-pound, 96-inch tall beam is carefully loaded onto a lowboy trailer attached to a heavy-duty tractor. Once secured, the transport vehicle slowly departs from the manufacturing facility, moving cautiously to ensure stability and safety. Behind the truck, an escort vehicle follows, providing continuous warning and guidance throughout the transportation route. Cranes play a vital role in Tokyo's major construction projects, where power, precision, and stability are of the utmost importance. These massive machines are seen operating at many large-scale construction sites, such as bridge construction sites, port developments, elevated highways, and urban infrastructure projects. At bridge construction sites, cranes are seen assembling massive steel beams, some weighing hundreds of tons. The video captures the delicate coordination between crane operators, assembly teams, and site engineers. Using radio communication and hand signals, they control every movement with centimeter-level precision. The wide tracks of crawler cranes ensure excellent ground stability, even on uneven ground or reclaimed land near rivers. As the long beams are lifted into position, the crane slowly rotates the lattice boom, while counterweights balance the load. Each operation is pre-planned, using digital simulations and detailed lifting diagrams. The combination of human expertise and advanced engineering allows Tokyo Juki cranes to handle complex structures safely and efficiently. In other sequences, the crawler cranes are deployed at Tokyo's busy harbor areas, where large modules for port expansion are lifted and positioned. Surrounded by containers, ships, and heavy vehicles, the cranes perform simultaneous operations in a highly restricted space. Their booms rise above the industrial landscape, and enormous hooks lower steel segments precisely into position. These operations highlight the importance of stability, load control, and operator skill. The film also shows the cranes working beside coastal piers, handling prefabricated concrete blocks used for breakwaters and quay walls. In these scenes, the crawler cranes are exposed to sea wind and harsh environments, yet their movements remain smooth and reliable. The video underscores the machines' durability and their crucial contribution to Japan's maritime infrastructure. As construction progresses, these crawler cranes become the backbone of activity, lifting heavy girders, steel trusses, and precast concrete elements into precise positions. Because they move on wide steel tracks, they can operate on soft or uneven ground where wheeled cranes cannot. Moreover, their ability to rotate 360 degrees and handle enormous loads with stability allows them to complete complex lifts in restricted spaces, typical of Tokyo's crowded construction sites. Whether working beside the Sumida River or at the port areas along Tokyo Bay, the cranes demonstrate remarkable versatility and reliability. Cranes are described not as individual machines, but as part of a coordinated system. Support trucks carry counterweights, cranes, and booms to the job site. Machinists assemble components precisely, bolt them in place, and check alignment before each lift. Engineers use tablets and drawings to confirm lifting capacity and crane configuration. Every process follows strict safety rules, reflecting Tokyo Juki's long tradition of discipline and professionalism. Operators inside the control cabin handle complex tasks through advanced control panels, hydraulic levers, and monitoring systems that display load charts, wind speeds, and crane angles. The quiet interior allows for full concentration during heavy lifting. Furthermore, cranes play a vital role in a high-rise construction, where they lift the massive steel frames and concrete slabs that shape the city skyline. Their precise controls and powerful lifting capabilities make them ideal for projects that require both strength and delicacy. The film also highlights the seamless coordination between crane operators, riggers, and ground crew, who work in unison to ensure safety and efficiency at every stage. Each lifting, rotating, and lowering motion reflects a combination of human skill and engineering excellence. The cranes are shown ready for the next day's work, their booms reaching toward the evening sky. The company's logo appears with the message that Tokyo Juki continues to support Japan's infrastructure with safety, technology, and dedication. Through this captivating presentation, viewers can truly appreciate the indispensable role of crawler cranes in shaping modern Tokyo machines that move the heaviest loads with elegance and precision, ensuring that progress rises safely above the skyline. The Pohorka Tunnel is a major infrastructure project on the D3 motorway bypassing the city of České Budějovice in the Czech Republic. It runs between the Suché-Verbné district and the municipalities of Dobrá Voda and Šubec, with most of the structure located in the cadastral area of České Budějovice 5. The southern portal lies within Šubec. This cut-and-cover tunnel, 999.5 meters long, consists of two tubes, each with a 2 × T 11.75 meters roadway width. The tunnel passes beneath the road to Dobrá Voda, the Dobrovodský stream, 2 local roads, and the 2-157 road. Construction began in April 2019, carried out by a consortium of Hochtief, Colas, and M. Silnice. Due to challenging geological conditions and high groundwater levels, the structure required the use of diaphragm walls and a roof slab before excavation. About 500,000 cubic meters of soil were used for backfilling. The tunnel officially opened to traffic on December 21, 2024. The County Route 104 bridge replacement project at Mankins Branch, located east of Georgetown in Williamson County, Texas, was undertaken to improve local transportation infrastructure and ensure long-term roadway safety. The new bridge was designed by Steger Bizzle and constructed by Chasco Constructors, 2 well-known firms in Texas specializing in civil and structural engineering. Construction began in September 2010 and was successfully completed in May 2011. During the project, the old bridge was demolished and replaced with a stronger, more durable structure designed to meet modern traffic and load standards. The new bridge was built using reinforced concrete and structural steel to withstand heavy vehicles and harsh weather conditions. The project involved several critical phases, including site preparation, foundation works, girder placement, deck construction, and approach road paving. Additionally, environmental protection measures were implemented to minimize disruption to Mankins Branch and its surrounding ecosystem. The construction team coordinated closely with local authorities to ensure safety and continuous traffic flow during the replacement process. By May 2011, the County Route 104 bridge replacement project was completed on schedule, providing a safer and more efficient route for residents and commuters. The successful completion of this project not only enhanced local transportation, but also reflected the dedication and engineering excellence of Steger, Bizel, and Chasco constructors.